Physical properties of organic compounds, solvent polarity and solubility. Have you got it? This quiz checks your understanding of how molecular structure affects the polarity of solvents and how the structure and polarity of organic compounds affects their solubility in water and organic solvents. It consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Consider the 12 compounds below. Which compounds would you expect to be soluble in water? Why? Pause the video while you consider this question. See if you can decide which ones are soluble in water. Okay, so what have we got here? A bunch of small molecules. I think your book states that a compound that has 5 or fewer carbons and an oxygen is likely to be soluble. So what do we have here in that category? Here's one over here. That's ethanol, ethyl alcohol, definitely soluble in water. How about this one? This is called methyl acetate. It's got only 3 carbons, 2 oxygens, definitely soluble. Here's one over here. You may not know the name of that yet, but that's acetic acid, and it's the main constituent of vinegar. So I think you know that vinegar dissolves in water, right? What else do we have with fewer carbons? Here's one right here. This one is called diethyl ether, and guess what? It's not soluble in water. So, surprise, surprise, this isn't a hard and fast rule. Here's one that isn't. Can you think of what might it be that would actually make this compound not so soluble in water, you suppose? I don't know for sure, but I would say that we don't have much of a dipole because of the canceling out of the dipole in left-right direction, and there is a slight dipole in the vertical direction here, but it's not very strong. So maybe that's enough to make it not so soluble. Well, what can we be sure really can't be soluble? Over here we have called heptane, 7 carbons, and that's the main ingredient in gasoline. Doesn't dissolve in water. This is naphthalene, no oxygens there. This one, how about this big one? What do you think? Pretty cool, huh? But this is cholesterol. And cholesterol is definitely not soluble in water. That's what craps out of your arteries and causes heart disease and such. Over here we have some compounds that look like they might come close, but this one has 6 carbons. It's phenol. This one has a nitrogen, okay, but not really too few, not really, and not it, but it has too many carbons. It's aniline, and aniline is not soluble. And this one over here is kind of interesting. You might know this compound. This is aspirin. What do you think? Is aspirin soluble in water? The answer is no, it's not. It does not dissolve in water to a substantial amount. I want to make the distinction between soluble and dissolves. We say that a compound is soluble if it dissolves to the extent of about 30 grams per liter. That means if we had 50 grams of this compound that's soluble and we had a liter of water, it would not all dissolve. Some of it would dissolve, but not all of it. And yet we would still say it's soluble. Likewise, if we had a very small amount of compound, like 50 milligrams. If we had 50 milligrams of aspirin, it would dissolve in 1 liter of water. But that still does not mean it's soluble in water, because 30 grams of aspirin does not dissolve in 1 liter of water. Okay, slightly different, soluble and dissolves. Okay, one more over here. Anyway, aspirin, not soluble. And this guy here, it's got about 6 carbons, but look at all the OH. So actually this one is soluble. So many places it can hydrogen bond. This is a sugar, like glucose, for example. All right, so cholesterol, no. Heptane, no. Naphthalene, no. Aniline, no. Phenol, no. Aspirin, no. Our soluble ones are these 3. Only these 3 right here. Right? Number 2, which of the following 6 solvents would you expect to be miscible with water? I don't know if you caught that meaning of miscible. Do you remember what that means? It means infinitely soluble in water, completely mixable at all proportions. Okay, you actually don't need to pause the video. I'll just give you 15 seconds. Look down the list. Think of the ones that will be miscible with water, do you think? And then I'll let you know. Okay, let's try this. Your book actually talks about acetone as being miscible with water. And actually, if you remember that, then you can get the rest of this problem, because this compound over here has to be even more soluble than acetone. It's an OH instead of a ketone. It's going to do much better hydrogen bonding even than acetone, and acetone is miscible in water. This is isopropanol. You may have seen it referred to as rubbing alcohol. This one over here is hexane, but it doesn't have any OHs. This one over here is CH2Cl2. We call it dichloromethane. It doesn't have any OHs or oxygens. This one over here, I bet you know the name of this one, ethanol or ethyl alcohol, miscible. So we have 3 miscible ones now. And then this one over here called phenol is not even soluble. So there you have it. Those 3 are our miscible solvents. Finally, here's a little challenge. Cocaine, with structure shown below, is not soluble in water. Take a look at that. Probably not too surprised, right? I mean, we have a lot of carbons, few oxygens, but no OHs. Imagine that you have the seemingly magic powers of a professional synthetic organic chemist, and you can change the functional groups of cocaine to anything you wanted. How would you change them in order to make a compound that would be soluble in water? How might you get cocaine into water without magic, using reactions you have already learned in this course? Take a look at the structure and give it a try. Okay, do you have any ideas? Basically, the idea is we want OH groups. So if you look over here, we have something that's kind of like an oxygen and maybe an OH, but what if we took off all this and made that into an OH? What do you think? And then how about if we go over here and we take off this methyl group and we turn that into an OH? That's kind of magical. Synthetic organic chemists know how to do that. Now we have an acid, we have an alcohol, we have a nitrogen. That's probably a good bet. What about this other part How could you do this using reactions you have already learned in this course? This section mentions that ionic compounds are soluble in water. So here's a question. Can we make this compound ionic without doing all this magical stuff? Well, you notice that this is a base. And if we were to treat this with hydrochloric acid, we could protonate that nitrogen. And now it would be a cation, and we'll have a counterion Cl minus, and this compound is ionic. So all we really have to do is add acid to the cocaine, and it will dissolve in water. Okay, so what have we got? Remember, the ability to accept and donate hydrogen bonds is critical in allowing an organic compound to be soluble in water. A general observation, not really a rule, is that a compound with 5 or fewer carbon atoms and an oxygen or nitrogen will be soluble in water. Ethyl ether is an exception to this rule due to its low dipole moment. And many small organic compounds with just a few carbons are actually more than just soluble. They're miscible in water, soluble in all proportions. Compounds like ethanol, isopropanol, and acetone. Well, I hope that helped, and I hope you've got it.